We're going to start with section 11.1, and this is about types of sequences. If you haven't done the sequences and patterns handout that we did together in class, you're going to want to start with that. So go back to the blog, download that, make sure you completed that, and then come back to this video. We're going to learn how to tell when a sequence is arithmetic, when a sequence is geometric, how to tell if a sequence is neither one, and then how to find the terms of a particular sequence. So first, just a definition of sequences. You've already explored these a little bit in your handout in class. A sequence is a list of numbers that go in a particular order, and they follow some kind of pattern, though the pattern might not be obvious right away. You guys dealt with some difficult sequences on that handout where the pattern wasn't always obvious. Here's one where the pattern is obvious. 2, 4, 6, 8, 10, 12, 14. So this is just the sequence of even numbers. The ... at the end indicates that the sequence is infinite, which means it continues on with that same pattern forever. We're going to use this very, very simple sequence to define some terms that we're going to use to talk about sequences for the rest of the chapter. So if we wanted to talk about a particular part of this sequence, each piece of this sequence is called a term. And so 2 would be the first term in this sequence. But instead of saying the first term or having to write the words first term all the time, we're going to note that with a T sub 1. So T just stands for the word term, and then the sub 1 tells me I'm talking about the first term. All the rest of the numbers in this sequence can be denoted very similarly. So T sub 2, T sub 3, T sub 4. This last one here is T sub 7, and a reminder that that just means that 14 is the 7th term in the list. We also need a way to just generally talk about any term in the list. So we're going to use T sub n to stand for the term in position n. N can be any whole number starting with 1, going up as high as you'd like. So if you wanted to say the 5th term in the list, you would say T sub 5. If you wanted to say the 100th term in the list, you would say T sub 100. And in general, T sub n just stands for the term in position n, where n can be any number that you'd like. The first kind of sequence we're going to talk about is an arithmetic sequence. And if a sequence is arithmetic, to get from one term of the sequence to the next, you're simply going to add the same number every time. So here's a really nice example of an arithmetic sequence. If you take a look at this sequence, you can see that to get from one term to the next, you're adding 6 every time. Another nice example of an arithmetic sequence. And to get from one term to the next, you might think of it as subtracting 4, but because we want to think about it as addition because it's arithmetic, instead we're going to think about it as adding -4. So if you add -4 every time, you'll get to the next term of the sequence. And then just for contrast, here's a sequence that looks like it might be arithmetic, but it isn't. You are still adding every time. To get to the next term of the sequence, you're adding 1, and then 2, and then 3, and so on. So you are still adding every time, and there's a pattern that you can discern. But because you're not adding the same thing every time, this is not considered an arithmetic sequence. And then we want to define one more piece of terminology. D stands for the common difference between terms. It's called a difference because if you take any term and subtract the one before it, you're going to get this number. So that's called the common difference. And similarly here, if you take any term and subtract the one before it, you'll get this number. So for each of these sequences, the common difference here is 6, and the common difference here is -4. You're going to use that a lot. So even though it says difference, the common difference is really what you're adding every time. They simply call it a common difference because if you take a term and subtract the one before it, you can find it. Geometric sequence is very similar in the way that an arithmetic sequence works. If it's geometric, to get from one term of the sequence to the next, you're just going to multiply by the same number every time instead of adding. So here's a really nice example of a geometric sequence where what you're doing is multiplying by 2 every time. This next sequence is geometric, and while your first thought may be that you're dividing by 3, remember that all division can be written as multiplication by a reciprocal. So instead of thinking that we are dividing by 3, we're going to think of it as multiplying by a third instead. And then another kind of geometric sequence. In this geometric sequence, you're still multiplying, you're just multiplying by a negative number. So here I'm multiplying by a -4. A positive turns into a negative, and then if I were to multiply by -4 again, you'd get a positive number, and these terms of this sequence will alternate positive and negative. That's fine. It's still geometric. What you're multiplying by can be a normal boring number, it can be a fraction, it can be a negative number. They can get more complicated than that. You'll see some examples in our classwork of geometric sequences where you're multiplying by a radical every time. But as long as you're multiplying by the same thing every time, that's called a geometric sequence. Just like in an arithmetic sequence, you have a common difference. In a geometric sequence, you have what's called a common ratio. There's two ways to think of a common ratio. First of all, it's just the number that you're multiplying by each time to get the next term in the sequence. So my common ratios for each sequence here are 2, a third, and -4. The reason it's called a common ratio, and the other way of thinking about it, is that if you take any term in this geometric sequence and divide by the one before it, you're going to get the common ratio. So something like 40 divided by 20, that reduces to 2, which is your common ratio. So that'll work for any of these. 3 divided by 9 is a third, and -64 divided by 16 is -4. So two ways of thinking about common ratio. So we've learned how to define sequences that are arithmetic and sequences that are geometric, but of course there are some sequences that are neither. Even though they follow some kind of pattern, that pattern might not be an arithmetic or geometric pattern. So let's look at a couple of examples. This first sequence, you might recognize it because it's similar to one of the ones we did on the worksheet. These are all perfect cubes. This is 1 to the third, 2 to the third, 3 to the third, and 4 to the third, and so it would keep on going in the same way, 5, 6, 7 to the third. If you were to assume that this is arithmetic, then to go from 1 to 8, you're adding 7. But if you add 7 again, that doesn't get you to the next term, so clearly this can't be an arithmetic sequence. Similarly, if you were to think that this is geometric, well, to go from 1 to 8, you would multiply by 8. But then multiplying by 8 again does not get you to the next term. We would just say that this sequence is neither arithmetic nor geometric. We're not going to try and classify it. Another one that you've seen, we talked about it on that handout, it's the Fibonacci sequence. Here you're adding something every time, but you're always adding the last two terms together. So 1 plus 1 is 2, and then 1 plus 2 is 3, and then 2 plus 3 is 5, and then 3 plus 5 is 8. Not arithmetic, not geometric, but it does follow a pattern. So these are both sequences that we would classify as neither arithmetic nor geometric. So now we'll do a couple of example problems. The instructions for this one are: first, tell whether each sequence is arithmetic, geometric, or neither, then supply the missing terms. If you take a look at this sequence, you can tell that to go from one term to the next, you're going to multiply by -1/2. And that'll work to get from -16 to 8 and from 8 to -4. So since we're multiplying by the same thing, that same common ratio every time, this is a geometric sequence. And the next two terms would be 2, and then multiply that by -1/2 is -1. This next sequence can be a little deceiving. While the top does follow a pattern of adding 1, and the bottom also follows a pattern of adding 1, that's not the same as adding the fraction 1 over 1, because in order to add those fractions, you would have to give them a common denominator. So really, you'd be adding 15 over 15, which would get you 19 over 15, which is not the next term in this sequence. So you would be correct in saying that you'd want to add 1 to the top and add 1 to the bottom, but that's not the same as an arithmetic sequence where you add the same thing every time. The next two terms are easy to find: 5 over 16 and 6 over 17, but because of the way that adding fractions works, this is neither arithmetic nor geometric. And finally, we'll talk about how to use a formula to find the particular terms of a sequence. So remember that T sub n just stands for the nth term in a sequence, where n can be any whole number starting with 1. So if you want the 100th term in a sequence, you would use n equals 100. So the instructions say find the first 4 terms of the sequence with the given formula, then state whether the sequence is arithmetic, geometric, or neither. We'll start this with n equals 1. So the first term is 13 minus 4 times 1 because n is 1. So the first term of this sequence is 9. Then n equals 2 will give us the second term. So t sub 2 is 13 minus 4 times 2, which is 5. Similarly, the third term is 13 minus 4 times 3, which is 1. And then lastly, the fourth term is 13 minus 4 times 4, which is negative 3. So based on what we just did with the formula, the first 4 terms of this sequence are 9, 5, 1, and negative 3. We can see that there's a pattern to these, that to get from one term to the next, you're subtracting 4 every time, which means that based on the pattern we've seen, this is an arithmetic sequence. All right, same instructions. We're finding the first 4 terms of the sequence. So the first term, we'll use n equals 1. 2 times 3 to the first is 6. For the second term, using n equals 2, we have 2 times 3 squared, which is 2 times 9, which is 18. For the third term, we have 2 times 3 to the third power, which is 2 times 27, which gives us 54. And for the fourth term, we have 2 times 3 to the fourth, which is 2 times 81, which is 162. So the sequence we end up with is 6, 18, 54, 162. And if you look at how to get from one term to the next, you are multiplying by 3 every time. And because that multiplication is consistent, we have a geometric sequence. So now we're not looking at the pattern between these terms. We're going to look at the pattern between the differences between these terms, and I'll show you what I mean. The difference between 1 and 2 is 1. Between 2 and 6 is 4. Between 6 and 15 is 9, and between 15 and 31 is 16. And you'll notice that those differences are a sequence of their own. In fact, that is the sequence of perfect squares: 1 squared, 2 squared, 3 squared, 4 squared. So because the differences follow a pattern, we can use that pattern then to generate a pattern above. So the next perfect square is 25. And if we add 25 to that, we get 56. And then the next perfect square after that is 36. And if we add that to 56, we get 92. So we're not looking at a pattern between the terms, but their differences. And we're all done. That's the end. So go fill out the Google form for your homework, and we'll work on some of these problems in class the next time we meet.